So we have talked about the idea of double integration methods, the procedure. So now let's look at how to using double integration method to come out deflection calculation. So here, look at here, we have a cantilever beam. The length is L, and we apply a concentric load at the free end of the point B. So can we using double integration method to calculate the deflection of the point B and the rotation of the point B? So how to do it? So this is a procedure. So we have the differential equation. This differential equation, dy dx squared equal to mx over ei. So this is the equation to calculate the deflections. So at the beginning, we see there is a function we need to determine is the bending moment functions. So mx. If we don't know mx, if we don't know the expression for mx, we cannot come out the expression for the deflection. So the first step is calculate the function for the bending moment. So if we want to calculate if expression for bending moment, so we need to build up a free body diagram. So first of all, let's using the method of section, and we arbitrarily cut a section on this beam A to A. So if we cut this A to A, so we have, if we just draw the section here, A to A, and we have a concentric node P, so this point is B. Okay, so here the coordinate systems is built like this. The coordination system shown here is built up like this. So the orange of these coordination systems is at point O. So start from O. So if we do the analysis on this small segment, so then if we say this is coordination system over here, X, okay, this is O, Y. So if we cut through this cutting is at the location of X, then from this cutting to B, the dimension will be L minus X. Okay, so this is this segment. So now we want to know the bending moment on this beam. The bending moment on this beam. So if we draw the bending moment, then bending moment is M. Okay, so we can express the M in this segment. So if we say if we write down the moment equation of equilibrium at section A to A. So if we assume for this equation, the positive direction per bending moment is clockwise. So equal to 0. So the bending moment, so at this section A to A, the bending moment M is positive, and we have the other bending moment comes to the concentric node P. So concentric node P have bending moment clockwise, so it's positive as well. So plus P, and the lever arm for the concentric nodes to the cutting section A to A is L minus X. So P minus P times L minus X equal to 0. So M equal to minus PL minus X. So this is the function of mx. So after we have these functions, then we can calculate the deflection. So for this equation, we write down here. So we can write down like this. So EI, we just put EI to the left hand side. So EI d square y dx square equal to mx. So mx is equal to minus plx. So look at here. So now we go through the same procedure. So the first integration will be ei dy over dx equal to 0 to x pl minus x dx plus c1. Okay, so if we just evaluate this equation, we will have, so if we open this, if we evaluate this integration term, we will have minus plx plus 1 over 2 px squared plus c1. Okay, so ei dy over dx. So we say dy over dx is slope. So we say slope is approximately equal to the rotation here. So we see ei theta equal to this equation. So this equation is the equation for the slope or equation for the rotation. After we have this, so we do second integration, then we have ei y. Second integration 0 to x squared dx times c1x times c2. Okay, if we evaluate this integration, so we can evaluate this integration is quite straightforward. We got minus 1 over 2 plx squared and times 1 over 6 px cubed and plus c1x plus c2, and this is eiy. So we got two equations. So this is equation for deflection. So this is equation for rotation or equation for the slope. Then, as I said, we have two constants, C1 and C2, need to be determined. So, as I said, to determine these two unknown constants, we need to using the boundary condition. So, boundary condition B, C, boundary condition. So, the boundary condition that is a cantilever beam at point A, x equals 0, y equals 0. There's no deflection at point A. Also, there's no rotation at point A. So the rotation theta is equal to 0. So now we write down the boundary condition here. So x equals 0, y equals 0. And also x equals 0, theta equals 0. Okay, this is two boundary condition. So if we apply the first boundary, so we apply the first boundary condition to the equation of deflection, we get, so y equals 0, so left hand side is equal to 0, so x equals 0, so this term 0, this term 0, this term 0, then C2 equals 0. So we come out C2 equals 0. And here then we need to look at the second boundary condition, x equals 0, theta equals 0. So x equals 0, theta equals 0. We come out, so left hand side theta equals 0 is 0, x equals 0. So this term 0, 0, and C1. So C1 equals 0, C2 equals 0. So the last, the equation is EIY equal to minus 1 over 2 PL x squared plus 6px cubed. So C1 equals 0, 0, C2 equals 0, so there's no more terms. So this is equation of deflection. So equation of deflection. And also we got the equation for the rotation. So we have EI theta equal to PLX plus 1 over 2 px squared. C1 is equal to 0. So this is equation of the rotation. So we need to know what is delta B or what is theta B. So delta B is the deflection at the point B. theta b is the rotation at the point B. Point B, x equal to L. So point B, x equal to L. So once we know x equal to L, we will move to here. So x equal to L, so we can calculate the deflection. So then x equal to L. So the deflection B, YB or delta B is equal to, we move back EI to right hand side, 1 over EI minus 1 over 2 PL times L squared times 1 over 6 PL cubed. So if we evaluate these terms, we come out the value is minus PL cubed is 3EI. So this is the deflection at the point B, delta B. And theta B is x equal to L, theta B equal to, so theta B we must use in this equation. So same, we have, we move EI to right hand side, 1 over EI minus PL squared plus 1 over 2 PL squared is equal to minus PL squared over EI. So this is the, so we have a 2, so don't forget 2 over here. So here we have the result. The result for rotation is this, and for the deflection is this term. So we see there's a minus, that's minus over here, minus the negative sign over here. That means your deflection is negative, your rotation is negative. So if we look back here, so your deflection is negative because based on this coordination system, so the x 0 points, so the y, so above this x-axis is positive because this deflection is below the x-axis, so it's negative. Makes sense. Also, this rotation is negative, so you're on this direction. If go up on this direction is negative, so it's negative. So go up is positive, then it's negative. Theta B is negative.